Okay, welcome back to Mr. Francois Physics, and we have another thing to teach you about is circuit resolution. Now, what that means is that we're going to be able to boil down a circuit, not the same way that you boil carrots, but boil down a circuit so that we can find out every value that we need to know about anything that's in a circuit. So let's begin. So let's say we have this example here where we have this wonderful set up circuit for us where we have 9 volts on our battery over here, and we also have a 1 ohm resistor here, a 3 ohm resistor, a 2 ohm resistor, and a 4 ohm resistor. So, it's a little bit complex, but it's also nice and simple at the same time. So how do we want to break this down? What can we do? Well, one of the first things that we can do is if we know every resistance apart from the total, we are able to find out what the total resistance is, because we have rules for how resistance works. So let's boil this down. So the first thing that you should try to do is try to identify what's in series and what's in parallel. Now, I highly suggest, if you want to try this out, stop the video right now, try figuring out every voltage, current, and resistance for the total of the circuit and for every component. Okay, so stop the video now and try it, and then come back, and now you should be back. So what you want to do is you want to try to break this down. You should identify what is in series and what is in parallel. So one of the first things that we should look for is series or parallel, and we see here between the 4 and the 2 here, the current that flows into the 4 this way goes down through the 2 as well. So this is our definition of series, right? So if they are in series, we can combine them together, and our resistance rule for in series is that the total in series is equal to the first resistance plus the second resistance, and so on for however many that you have. In our case, we only have 2, so 4 plus 2 gives us 6. So we can combine those, we replace them. We don't lose anything from the circuits except for that resistor. We combine them and make them just one resistor, which is perfectly fine. That's okay. Now, we've just created this new simplified diagram. You break it down as I have shown you in the resistance video, and what we want to do is we want to combine these two, because the 3 and the 6 here are in fact in parallel with one another, because they have a branching off point that separates them, so the current changes, the current splits up. Some of it goes through the 3, some of it goes through the 6, and they're the only resistors on each branch. So here's a branch and here is a branch, right? So we want to combine these so that we have one combined resistor that we talk about now. Here we're actually going to get rid of this branch here, okay? Because when you combine a parallel, you're breaking it down into one thing, so we don't have 2 paths anymore, we just have one. And we want to use our resistance rule for parallel, which is 1 over the total is equal to 1 over the first resistance plus 1 over the second resistance, and so on for however many branches that we have in parallel. As long as they are all the only resistors on each branch and they all split off from the same point, or effectively the same point, then we can add them up in parallel all at once. Okay, so what does this look like when we do this out? 1 over 3 plus 1 over 6 ends up giving us 4 over 6, which is 2 over 3, but it's 1 over the total, so when we bring them together, it's not 4 over 6, ends up being 2 here. Okay, now it's 2 here, so we combine them, we ended up there, and we end up with 2 ohm resistor and 1 ohm resistor. Again, these are in series. We should be able to see that. The current that flows out of the battery goes into 1 and then goes into 2, so all the current from 1 goes into 2, so that makes it series. We add them together, and we find our total resistance is this 3 ohms right here, which is very nice. So let's take a look back at how this was for us. So we started off with our big circuit up here, and we broke it down, and I highly suggest making these little arrows in between them so that you can tell what way you went. And we went down a step and down a step. Now, we're not going to be able to get immediately back from this point right here all the way back up to here. We can't shortcut it, okay? If we could shortcut it, then there would only be that one simplified diagram, but we can't. We have to take our individual steps back. So let's go back to what we have here. Now we have 9 volts across this resistor, so focus solely on your last simplified diagram. There are 9 volts across here, okay, because all the voltage is, being applied to this one 3 ohm resistor. So we have 9 volts here, and we know because we have this wonderful, wonderful rule called Ohm's law, okay? And Ohm's law is a relation between the 3 values, that voltage is equal to current times resistance. That's what this means. So since I have the voltage and since I have the resistance, I can find out what the current is. And the current is actually 3 amps because I rearrange this so that I have I equals, and it becomes V over R, which means 9 over 3, which in fact means that I have 3 amps, right? Don't forget your units, okay? Because if you are unitless, you are pointless, okay? So we have 3 amps on here. Excellent. Okay, well, okay, so we have this. That's wonderful. Good to know. Well, okay, so we know about the simplified diagram. Well, let's backtrack. Let's find our way back to where we were. So if we look at this, we went from here to there, right? Well, now instead we are going to be going backwards, but we're not going alone. We're not going empty-handed because this resistor here on our last simplified diagram actually came from these two, right? We combined these 2 resistors in order to find out about this resistor, to find what its total is. So this represents this new resistor, this last resistor represents the combined amount of these 2 that came before it. And those 2 that came before it are connected in series. So we have to ask ourselves, well, what can we bring back? I mean, we can't bring back the resistance, and we don't really need it because we already know, okay, this was, 1 ohm and this is 2 ohms, right? So if it's 1 ohm and 2 ohm, we can't really bring back the resistance, so we have to bring back something else. Let's see what happens in series and what happens in parallel. Well, let's look back at what I know. I know that the current in total in a series is the same as the current at one component and the same as the current at the second component, and so on. And I know that for voltage, the voltage total of a series is equal to the voltage 1 plus the voltage 2 plus and so on. So if we take a look at the voltage here, we see that it's not really helpful to us, not at all, because in order to be able to solve for, well, anything in here, I would have to know everything else, and I don't know everything else. I don't know what the voltage is here, and I don't know what the voltage is here. So I've got at least 2 unknowns that I don't know, and I don't have a way of finding out for. So what I have to do is I have to now go, okay, well, what can I bring back? Well, thankfully we have this other value that I can bring back. It's the current, because the current total is equal to the current at every point along the series, right? The current in total of the series is equal to the current anywhere along that series. So that means that since I know the total here, I can bring that back with me to over here. So that means this is 3 amps and this is 3 amps. Oh, well, that's rather nice. I mean, that's wonderful. Okay. And also, hey, look, now we have 2 values. 2 values means we can find the third value from that wonderful, wonderful equation from Ohm that V equals IR. So since I know the current and I know the resistance in each case, I multiply them together and I will end up getting my voltage. So 3 amps and 1 ohm ends up giving me 3 volts. 2 ohms and 3 amps ends up giving me 6 volts. Okay, that's wonderful. Well, now that we have that, let's backtrack again. So we had this, and we came, this way, right? And now we ask ourselves, well, what do we have? What do we have? I mean, yes, okay. Well, I know that the 1 ohm is still 3 amps, and that's still 3 volts. That's good, wonderful. Yeah, okay, cool. But what do I know? How can I split this up? Because it came from a parallel. Well, let's look at our parallel rules. We know that current in a parallel in total is equal to the current of one branch of the parallel plus the current of the second branch of the parallel, and so on. And voltage in total is equal to the voltage of the first branch, which is equal to the voltage of the second branch, and so on. And so now we look at this and we go, okay, well, I chose the equivalent equation last time. Let's do it again this time, because that's what we can actually bring back. So this resistor here represents these ones here, right? So let's bring our voltage back. So we take our voltage and we bring it back, and we apply it over here, and we know this is 6 volts and this is 6 volts, and that's wonderful. Because, again, hey look, we know two things. So I divide them because we know that V equals IR, but I want to solve for I again, so I rearrange this. I is equal to V over R. So that means that this is 1 amp and this is, in fact, 2 amps. Okay, cool. So now I know everything about this. Well, let's bring it back again so that we can go all the way back to the original. So I know everything here. I know what 1 is. I know 1 is still 3 volts and 3 amps on that 1 ohm resistor. I know that the 3 ohm resistor has 6 volts across it and has 2 amps. But now, again, we have this 6 ohm here. That actually represented a series, right? And if we recall back to what we just did before when we had the series, we brought back the current. So the current gets brought back, and it's 1 amp, and this is 1 amp. And so that means I can calculate the voltage because I know both the resistance and the current, which means I can find the voltage through multiplication. So this is 2 volts, and this is 4 volts. And so I can list all of these out just by what the resistance is. So I have a 1 ohm resistor, I have a 2 ohm resistor, I have a 3 ohm resistor, 4 ohm resistor, right? And I want the total. I know that my total ended up being 3 ohms, right? For resistance. And if I just made a quick chart out of this, I can say, okay, well, I just copy all of my data over. So the 4 ohm had 1 amp running through it. The 3 ohm had 2 amps running through it. The 2 ohm had 1 amp running through it. The 1 ohm had 3 amps running through it. And we had 3 amps in total. And then just to fill in the last of my chart, I have a voltages. The 4 ohm had 4 volts. The 3 ohm had 6 volts. The 2 ohm had 2 volts. And the 1 ohm had 3 volts. And in total, the total of this was, of course, 9 volts because that's what was given to me. So there you have it. We now have all the values that we could possibly want, and this has been your instruction on complex circuits and breaking it down. So please feel free to leave a comment if you have one in the description or underneath the description here. Like it if you want, and if you need it, ask me any questions when you come into class. Have a great rest of your day.